Now that we've looked at how to do nodal and mesh analysis in the frequency domain, let's now look at some of our more advanced circuit analysis techniques. And let's first talk about circuit transformation techniques. So first of all, source transformation. So source transformation is effectively still the same process we saw before in the time domain, only now we're doing it with phasors and with impedances instead of with standard sources and with resistances. So if we've got a source like so, composed of a voltage source in series with an impedance ZS, there exists a transformation such that we can go to I sub S in parallel with that same source. And as far as anything is connected across terminals A and B, we'll get exactly the same behavior as far as any load. And of course, in this case, Vs is equal to Is times Zs, and Is is equal to Vs over Zs. So no surprise there. We've actually seen this kind of behavior before, this kind of transformation. And if I wanted to do a simple example, I could, for example, have a voltage source. This is 10 volts. Notice that's the rectangular form, so that's 10 plus J0 volts. And if I have that connected to a 10 ohm and a J10 ohm impedance, and notice that impedance has to be positive because that's an inductor, then I can show that this can be transformed such that I have a current source which is equal to 10 divided by 10 plus J10. And if I plug that into Mathematica, what I'm going to get is this is equal to 0.5 minus J 0.5 amps. And then that'll be in parallel with my resistor and my inductor. So here's our simple source transformation, simple example of that. As we can see, there's nothing here that is surprising, exactly the same technique. We're just now doing it with complex numbers. Now, of course, along with this source transformation, we have more sophisticated techniques, Vernons Theorem, Norton's Theorem. So just as in the time domain, as long as we're dealing with linear circuits in the frequency domain, then we can show that this must be true. Given a frequency domain linear circuit, we can show that there must exist a transformation such that this can be transformed either into a Thevenin equivalent or a Norton equivalent circuit. And of course, there exists a transformation between Thevenin and Norton. And of course, that is due to source transformation. So in this case, ZTH will be equal to Zn. The Norton and Thevenin equivalent impedances are the same. And In is equal to VTH over ZTH. And VTH is equal to In times Zn. So exactly the same types of equations we saw before. We're just now dealing with complex numbers, with phasors and with impedances, as opposed to time domain sources and resistors. Okay, so this principle is exactly the same. So let's just work through a couple of examples to demonstrate that. Let's find a Thevenin equivalent circuit of the following. All right, so we want to transform this. We're going to use exactly the same type of technique we did before. So first of all, if we're going to find the Thevenin equivalent, we have to find the open circuit voltage. So let's find the open circuit voltage in the phasor domain, or in the frequency domain. And so in this case, we want to find VOC, and I'm going to go ahead and ground the bottom node. That makes this top node voltage VOC by definition. This becomes 10V1 at that node because it's defined by that dependent source. V1, since the way I've defined V1, I can just call that node voltage there V1. And 120 volts at 0 degrees phase angle will be equal to 120 volts in rectangular form. And therefore, I've got 120 volts at that node. Now I write my KCL equations. And so in this case, I'll pick my current direction going this way. Obviously, I don't want to fight that V1. And this way. And this way. And so I write KCL equation here and also with the VOC node because I need to know the value of VOC. And so my essential node first is that for my V1, I've got V1 minus 120 over 12 plus V1 over 60 plus V1 minus VOC over minus J40 is equal to 0. And for VOC, we'll have that V1 minus VOC over minus J40 must be equal to VOC minus 10V1 divided by 120. Now you notice there's a dependent source variable. Where's my dependent source variable equation? Well, V1 is already a node voltage, so the dependent source variable is that V1 is equal to V1. So in this case, I don't really need to write an equation because it's a trivial result. I've got two equations and two unknowns, and if I solve, what I will get is that VOC is equal to 784 minus J 288 volts, which will be equal to 835.22 at a phase angle of minus 20.17 degrees volts if I want it in polar form. And of course, that is my Thevenin equivalent voltage, VTH. All right? So, there's my Thevenin equivalent, no different. I just find the open circuit voltage. Now let's find the Thevenin equivalent impedance. So in this case, I'm going to take my circuit and I'm going to zero out that voltage source. So now this is all ground along the bottom. And then I'm going to connect a source to the output, an independent source. Now, what's the value of an independent source I can use? Okay, I'm going to use the same concept of source driving. So I'm going to specify IT. I'm going to find VT, and these are both phasors. So what's a good value I can pick for IT in the phasor domain? What about 1 at a phase angle of 0 degree amps, which is equal to 1 amp? So exactly the same value. Use 1 amp or 1 volt, which is just a rectangular form of a phasor. And so in this case, this is 1 amp. And now I can go through and calculate the values I need here. So now with VT defined, this top node becomes VT. And now I can go through and write the equations for this. And so in this case, V1 over 12 for my V1 node plus V1 over 60 plus V1 minus VT over minus J40 is equal to 0. And for my VT node, I have that V1 minus VT over minus J40 plus 1, both going in, must be equal to VT minus 10V1 divided by 120. And now I can solve for this. And if I do, what I will get, two equations, two unknowns, I will get that VT is equal to 91.2 minus J 38.4 ohms. And given this, that means that ZTH must be equal to VT divided by 1 amp is equal to, actually I should say this was volts, pardon me. So this becomes 91.2 minus J 38.4 ohms. There we go. So there's my Thevenin equivalent impedance. So what does this circuit look like when I draw the Thevenin equivalent? It looks like this. It's a 91.2 ohm resistor. That's the real part. The imaginary part is minus J 38.4. Because it's negative, it's got to be a capacitor. So that's minus J 38.4 amps. And my voltage source is 784 minus J 288 volts. And so here is my Thevenin equivalent circuit in rectangular form. Now from here, given the Thevenin equivalent, I can easily find the Norton equivalent. all I have to do is apply the source transformation technique. And so I'm going to have a source which is equal to 784 minus J288 divided by 91.2 minus J38.4. And that will be equal to 8.431 plus J 0.392 amps. So that's the value of my current source. And of course, I still have the same value for the impedance between A and B. And so this will be 91.2 ohms. And this will be minus J 38.4 ohms. And so there is my Norton equivalent circuit. Nothing different here. Exactly the same techniques you've seen before. Absolutely nothing that you need to do differently beyond learning how to do this in complex numbers. And of course, having a tool like Mathematica or MATLAB makes this much easier. Not the kind of thing you want to do by hand. In fact, I really recommend this very much when you're working these types of problems. Never try to do any type of reduction by hand. It's too easy to make a mistake when you're dealing with complex numbers. So instead, just put it into Mathematica, let Mathematica do the work for you. Okay, now, one last question here. If you were asked what the time domain equivalent circuit was, so for example, if you were asked to convert this into the time domain of the Thevenin equivalent, what would you get? All right, so for the time domain, in order to go to the time domain, you have to know what the omega is for the circuit. So you have to be given a value of omega. So let's say that omega is, we're told that omega is 100 radians per second. So what's the time domain equivalent of the Thevenin equivalent circuit? Well, in this case, let's go to the polar form for our voltage source. And so our voltage source will be equal to 835.22 times cosine 100t minus 20.17 degrees volts. So we just go straight to the rectangular domain, from rectangular to the polar domain, and then simply pull out the magnitude and the phase angle and plug it in here with omega equal 100. Then we still have the resistor. That doesn't change. Still 91.2 ohms. And we also have an impedance for that capacitor, and minus J38.4 must be equal to minus J divided by 100 times C. And we solve for that. And what we get in the time domain is 260.4 microfarads. And there's our result. So once you solve in the frequency domain, going to the time domain is this simple. Now please note, an impedance in the time domain is going to be a resistance and a capacitor, or a resistance and an inductor. It's not going to be a sinusoid. This is a mistake students will make. They'll take a rectangular form of a impedance, convert it to a polar form, and then try to write something like this. They'll try to write Z of t is equal to some magnitude times cosine 100t minus theta sub z for that impedance. And then they'll try to say there's something like this in ohms. That makes no sense. There's no such thing as a sinusoidal time domain resistance or anything else like it. So this doesn't make any sense. As we said before, an impedance is not a phasor. A phasor means you're representing a voltage or a current in terms of a sinusoid. But an impedance is actually real components with values of ohms in the time domain as well as the frequency domain. And then when you convert inductors and capacitors, then you're going to convert to farads or henries for the units. So keep this in mind. Don't make a mistake like this if you're asked to do a transformation. Okay? So this has basically just been a quick little review of Thevenin, Norton, and also source transformation. Once again, there's no difference, no change in the techniques you see here. All you're doing is you're using complex numbers to solve.